This is the first video in a series that I'm making for a course in abstract linear algebra. And by abstract linear algebra, I mean we'll be doing everything with proofs. And I think this has the advantage of practicing proofs at an early stage in mathematical education, as well as gaining a fuller understanding of the subject. I think if you understand linear algebra from an abstract viewpoint, you can apply it to a concrete viewpoint. Whereas if you understand it only from a concrete setting, it's hard to abstract that, or it's not as obvious how to abstract that. So for the first couple of videos, we won't be looking at the standard objects of study in linear algebra. We will instead be looking at some background material which will help us study linear algebra more abstractly. So today I want to look at sets and functions. So let's say we have two sets A and B. A function from A to B, which we'll write like this, so it'll be f colon A to B, is an association of each element from A, I'll call that little a, with exactly one element from B, I'll call that little b. And the standard notation is that little b equals f evaluated at little a. So you're probably familiar with this type of notation from calculus. And so this set A is called the domain of f, whereas this set B is called the codomain of f. You might think that this set B should be called the range, but that's actually reserved for a subset of B, which we'll talk about a little bit later in the video. So here are a couple of picture examples of functions and non-examples of functions. So in each of these, the blob on the left is the domain and the blob on the right is the codomain, and the elements are indicated by these dots. So here's an example of a function right here. Notice that this first element is associated with exactly one element of the codomain. It's this one. This second element is also associated with exactly one element. It's this one. And this third element is associated with exactly one element. That's this one. Notice the second and third element are associated to the same element, but that's okay because they are each only associated with one element. Furthermore, we see that this third element of our codomain is missed. That's also okay. There's nothing about the elements of B being associated with one element from A. Here's another example. So here this first element is associated with the first, the second with the second, and the third with the fourth. So the third element over there in the codomain is missed, but again, that's okay. So here's a non-example. It's a non-example because this second element is associated with two elements of the codomain. But since each element should be associated with exactly one, that makes this not a function because 2 is not equal to 1. Here's another non-example, and this non-example comes from the fact that this third element down here is not associated with any elements of the codomain. So it's associated with exactly 0 elements of the codomain, but 0 is not equal to 1. So that makes this assignment and this assignment not a function, whereas this assignment and this assignment is a function. Okay, so now that we've reviewed the definition of a function, as well as the parts, the domain and the codomain, let's look at some other definitions. Now I'd like to look at the notion of the image of a function, also known as the range of a function. So given a function f from A to B, the image or the range, so those are synonyms of f, well, it's denoted by this capital I-M of f, or by f evaluated at this entire set A. And that's defined to be the set of all points in B such that B equals f of little a for some a and little a. You can also write it as the set of all elements f little a, where a runs through all of the elements of capital A. So these are equivalent definitions of the image. In both cases, let's notice that this is a subset of B. It need not be the whole set of B. So this is how we talk about the difference between the range and the codomain. So let's look at a couple of basic examples. So if we have f from R to R. In fact, all of these will be functions from R to R. So the first one is defined as f of x equals x squared. So in this case, the image of f will be all non-negative real numbers. So we can write that as a half open interval like that. That's because we can't achieve any negative numbers via squaring without using complex numbers. Now, what about if we've got g of x equals sine x? Well, if you recall from calculus, or maybe from a pre-calculus class, sine is always between -1 and 1, including -1 and 1. So that tells us that the image of this function g is the closed interval -1 to 1. Finally, if h of x is the exponential function e to the x, the image is the open interval 0 to infinity. That's because e to the x is always positive. We can achieve any number that is larger than 0, but we cannot achieve 0. Just think about the horizontal asymptote to the left of this e to the x function. So we need a couple more definitions and we'll keep going. Now we're ready to look at the notion of an injective, surjective, and bijective function. So here we'll start with a function from a to b, where those are arbitrary sets. F is injective whenever we have the equation f of a equals f of a prime, implying that a is equal to a prime. Next, it's surjective if for all b and b there exists an a and a, such that f of a equals little b. So let's notice that that is equivalent to the image of f being the whole set capital B. Finally, it's bijective if it's injective and surjective. So the first example that I'd like to do is this function from the real numbers -1 to the real numbers -1. So this is just all real numbers where we have excluded the number 1. And it's defined as this rational function. So we have f of x is x minus 2 over x minus 1. We want to show that this is bijective. So that means we need to show that it's injective, and we need to show that it's surjective. So let's get going. So how do we show that it's injective? Well, let's suppose we have two elements of the domain. So I'll maybe call those elements x and y, just so that I don't have to worry about primes over here. So we have x and y in the domain. So that's going to be r excluding 1. But they satisfy the rule that f of x equals f of y. And now we'd like to end with x equals y. That means we've satisfied the rules of this definition, and thus we have an injective function. So let's take this, f of x equals f of y, and rewrite it using the definition of f. So that means we have x minus 2 over x minus 1 equals y minus 2 over y minus 1. And now we'll manipulate this until we hopefully have x equals y. So let's cross multiply both sides. That will give us x minus 2 times y minus 1 equals x minus 1 times y minus 2. Again, just cross multiplying like I said. Now we can FOIL this out. We'll get x times y minus x minus 2y plus 2. So that's just from minus 2y here, minus x here, -2 times -1 is plus 2. And then over here, we'll have x times y minus 2x plus 2. But now we've set up some simplification that can occur. Notice that this xy here can cancel with this xy here. The number 2 here can cancel with the number 2 here. And then we can maybe move all of the x's to one side of the equation and all of the y's to the other side of the equation. Maybe we'll move this -2x over here, and then likewise we'll move this -2y over here. So adding 2x to both sides will give us x on the left-hand side. Adding 2y to both sides will give us y on the right-hand side. But that's exactly where we needed to end for this thing to indeed be injective. And now let's move on to the proof that it's surjective. Now we're ready to prove that this thing is surjective. And this actually requires a little bit of scratch work. Well, maybe requires isn't quite the right word, but this is the way I like to do it with some scratch work. So let's say our goal is to find some x in R minus 1 such that f of x equals y, where y is arbitrarily chosen, again, from R minus 1. But as you'll see, we'll sort of do some calculation over here and then write it in the correct order over here. Okay, so this means we need x minus 2 times x minus 1 to equal y. Cross multiplying, that leaves us with x minus 2 equals xy minus y. Now we'll move all of the x's to one side of the equation and all of the y's to the other. That leaves us with x minus xy equals 2 minus y. We can factor an x out, leaving us with x times 1 minus y equals 2 minus y. Now dividing by 1 minus y, we see that x equals 2 minus y over 1 minus y. We can multiply by -1 in the numerator and the denominator, leaving us with y minus 2 over y minus 1. So that's looking good. And that tells us in order to achieve an arbitrary number y, we have to choose this value for x. Okay, so let's do that. So let's suppose that y is arbitrarily chosen from the set R minus 1, and we'll set x equal to this number that we calculated over here, y over 2 minus y minus 2 over y minus 1. Now notice this looks an awful lot like our original function, but that's really just lucky. That actually means that this function is an inverse of itself. This is not something that you would expect to happen. Again, this is just like kind of the luck of the construction of this function. Okay, so now that we've set x equal to this, we'll say something like this. And now we'll notice that if we evaluate this value of x with our function, we should get y. So let's see that. We have f of x equals, well, it's x minus 2 over x minus 1, but that's going to be y minus 2 over y minus 1 minus 2. Again, replacing all of the x's with this y minus 2 over y minus 1. Then we have y minus 2 over y minus 1 minus 1. So that's looking good. Now we can simplify this by taking the entire numerator and the entire denominator and multiplying by y minus 1. So that's going to leave us something like y minus 2 minus 2y plus 2. That's occurring in the numerator after distributing this minus 2 onto both of those terms. And then in the denominator, we'll have y minus 2 and then minus y plus 1. That's from distributing that minus 1 through. But let's notice that the numerator simplifies to just y, the denominator simplifies to 1, so we have this is equal to y. And that's what we needed to end up with in order to show that this is surjective. So that means we've shown that it's injective and surjective, which means it is indeed bijective. Let's look at another example of a function, which is in fact neither injective or surjective. We'll check that it's not injective, but it also has a little bit more interesting of a domain and codomain. So for our next example, let's suppose we've got a function whose domain is the set of all differentiable functions. That's sometimes called C1R. And then the codomain is the set of all continuous functions. That's sometimes called C0R. And the function is defined by just taking the derivative. So let's notice that this guy is definitely not injective, and that's because there are multiple functions that have the same derivative. And that comes from the fact that the derivative of a constant is equal to 0. So this is because the derivative of a constant is equal to 0. This is for all C in R. So for example, we have the derivative with respect to x of x squared plus 3 is equal to 2x, but that's the same thing as the derivative of just x squared. But we know that x squared plus 3 is not equal to x squared as a function. So that means we do not satisfy this definition of injectivity over here. So that means this is not injective. And we won't investigate the surjectivity of the function. If you have any ideas whether or not this function is surjective, maybe post them in the comments. And so now we're going to look at composition of functions. Now we want to look at the most natural way to combine two functions, and that's via something called composition. So let's suppose we've got a function f from a to b and a function g from b to c. So we define the composition of these two functions, g composed with f. It starts at a and it ends at c with the following equation. So g composed with f evaluated at a is equal to g evaluated at f, which has been evaluated at a. We can write that as the following commutative diagram. So we've got a is being mapped to b with our function f. B is being mapped to c with our function g, and then the composition is the function that defines a map from a to c all at once that gives us the same value as following the long way around this diagram. So commutative diagrams are really powerful for looking at a lot of different things in math, and this is maybe a good first example of one of these. So now I want to look at the following standard result, and that is composition is associative. So let's suppose we have three functions. So we have f going from a to b, we have g going from b to c, and then we have h going from c to d. And what we'd like to show in order to show that this is associative is that h composed with g composed with f is the same thing as h composed with g composed with f. So that's what I mean by associativity, is that we can do these compositions with any groupings at all. Notice I haven't said anything about commutativity. And in fact, commutativity may not even make sense because we need this middle set to line up with the codomain of f and the domain of g. And so if A is equal to C, then we could compose them in the opposite order, but we can't always compose them in the opposite order. And when we can, it's often not commutative. So that's what we'd like to show. But notice the left-hand side and the right-hand side are both functions, and functions are equal if they're equal at every point in their domain. So let's show that. So let's suppose that A is an element from A, and let's send A through the left-hand and the right-hand side of these compositions. Okay, so I'll just write it like this. So let's note that H composed with G composed with F evaluated at A is equal to, well, let's notice that that's going to be H evaluated at G composed with F, which has been evaluated at A. Just working through that composition from outside to inside. But notice that that is H composed with G, which has been composed with F evaluated at A. Or I should say H of G of F of A. And now let's work through the other order. So also, if we start over here, so H composed with G composed with F evaluated at A, well, let's notice that that is equal to H composed with G evaluated at F of A. But that is exactly equal to H evaluated at G evaluated at F of A. And thus we've created a loop of equality starting here and then ending here. And then since this A is arbitrary, we have shown the equality of these as functions. So it may seem like nothing really went on, but we carefully use the definition of this composition in order to achieve this associativity. The next kind of obvious question is, how does composition interact with injectivity and surjectivity? And that's what we'll look at with our next result. So we're going to have two results that link together composition with injectivity and surjectivity. I should say two main results. Each will have two sub-results. So here's the first main result. So if we've got functions f from a to b and g from b to c, if f and g are both injective, then so is the composition G composed with F. Furthermore, if F and G are both surjective, then so is the composition. These easily combine together to say that if F and G are both bijective, then so is the composition. So I won't even write that down, but if we've proven both of these by the definition of bijectivity, which is gone now, but it was there earlier, you see that that happens immediately. So let's prove each of these. We'll start with number one. So let's suppose that F and G are both injective. and that we have the testing setup for G composed with F being injective. So in other words, we have some elements, A and A prime, which are from capital A, such that G composed with F evaluated at A is the same thing as G composed with F evaluated at A prime. So just to point out where we're going, what we'd like to end up with is that A is equal to A prime. That means this composition will indeed be injective. So now let's apply the definition of composition to both of these. So that's going to tell us that G evaluated at F evaluated at A is the same thing as G evaluated at F evaluated at A prime. But now, so that's by definition of composition. That's why we can do that step. Then we have F of A equals F of A prime. That's because G is injective. So that's the reason we can do that step. And then finally, that tells us that A equals A prime. And that's because F is injective. That's why we can do that step. But that's where we needed to end in order to achieve the goal of showing that this composition is indeed injective. Okay, good. Let's get rid of this and we'll do the surjectivity. We just got done showing this result about injectivity. Now we're ready to show a result about surjectivity. Recall that means that every element from, in this case, C, should be able to be written as an image of an element of G composed with F, given that G composed with F starts at A and ends at C. So that's something we have to keep in mind. So let's suppose we have an arbitrary C, which is in the set capital C. And now let's work backwards. Actually, maybe before we get started, our goal here, so maybe we'll write it like this is the goal that would end this proof, would be to find some A and some little a in A such that G composed with F evaluated at little a is equal to C. So let's work backwards one bit at a time. So since G is surjective, we have a little b in B such that G evaluated at little b equals little c. So that's from the definition of G being surjective. Then, since F is surjective, we have a little a in A such that F evaluated at little a equals little b. So I think we've achieved our path from little a to little c via these two applications of surjectivity. Now maybe we'll do this. Let's notice that if we take G composed with F evaluated at little a, that's the same thing as G of F of A, which is the same thing as G of B, given the way that we chose A. But that's exactly equal to C, given the way that we chose B. But that's what we needed in order to achieve the goal of showing that this composition is surjective. Let's get rid of this and we have one more result relating to composition, injectivity, and surjectivity. For our next result, we'll show that if G composed with F is injective, then F is injective. And if G composed with F is surjective, then G is surjective. Okay, so let's get going on this first one. So that means we want to start by supposing that G composed with F is injective, and we have A and A prime in little a with F evaluated at A is the same thing as F evaluated at A prime. Remember, that's our testing setup for deciding if little f is surjective or is injective or not. Let's recall that what we want to end up with is A equals A prime. And what we have as a tool is that G composed with F is injective. Okay, so now let's take this equation and we will evaluate both sides by G. So we've got G of F of A equals G of F of A prime. But then by definition of composition, that tells us that G composed with F evaluated at A is the same thing as G composed with F evaluated at A prime. But then, because G composed with F is injective, that tells us that A is equal to A prime, which is where we needed to end to finish showing that F is injective. Now let's show this other result. If G composed with F is surjective, so is G. So in order to show that G is surjective, we need to show that for all little c and c, there's a little b and b, such that G evaluated at little b equals c. We have as a tool that G composed with F is surjective. So let's suppose, like I said, G composed with F is surjective, and we have a little c in C. So what does that tell us? That tells us that there exists a little a in A such that G composed with F of little a equals little c. That's the surjectivity of G composed with F. But that tells us that G evaluated at F of A equals C. That's the definition of composition. But notice that F of A is in B, so maybe we should call that our little b. So let's set little b equal to F of A, and note that G evaluated at little b is exactly C by this equation right here. But that's exactly what we need in order to finish off this proof of surjectivity. Okay, so that's good. So let's end the results here. I'll clean up the board and leave you with a couple of warm-up exercises. So here are 3 nice warm-up problems related to sets and functions. So let's start with the function f from z to z cross z, given by f evaluated at n, so that's any integer, is equal to 2 times n comma n plus 3. So we need to recall that z cross z is all ordered pairs where each part comes from the integers. So determine if this function is injective and if it is surjective. Next, let's define a function f from r minus the number 2 to r minus the number 5 by f of x equals 5x plus 1 over x minus 2, and show that that function is indeed bijective. Finally, we've got this nice counting problem. So that is to count how many functions there are from the set capital A, capital B, capital C, capital D to the set 1, 2, 3, 4. Furthermore, how many of those are injective, how many are surjective, and how many are bijective? Okay, that's a good place to stop.